Inductors and Inductance, part 1 of 2 presentations. What we're going to be looking at in this presentation is inductors in industry, where we find them, factors affecting inductance, and how inductors will react when connected into a DC circuit. So, inductors in industry, where are they? Anything that is an electromagnet or that uses electromagnetism in some way, shape, or form will exhibit the physical property of inductance. Motors are a prime example of inductors in industry. Small transformers, such as CTs, are also examples of inductors in industry, as well as larger transformers, three-phase distribution transformers. These all exhibit inductance. Solenoids are another example of inductors in industry. A solenoid is identified by a movable solid core that moves with spring action back to its original place from its actuated location or position, which is due to electromagnetic flux from an electromagnetic coil. Solenoids are seen in doorbells as well as valves that are used to control fluids in piping systems. Relays and contactors also exhibit inductance. This is similar to a solenoid, however, the core remains in its fixed position and an armature moves, which opens and closes electrical contacts. And finally, another example of a transformer is seen in HID lighting or ballasts, which they're commonly known as, which have a capacitor and typically a larger transformer inside the connection housing. Line and load reactors are probably the simplest form of an inductor. This is a three-phase line reactor, and what it's used for is to improve the use and application of VFDs, variable frequency drives. This one is not hooked up to a motor yet, but all that happens with a line or a load reactor is that load current flows through, in series, a single coil of wire. This is how we typically show them when sketching. Typically, you'll have rounded bumps with two horizontal parallel lines on top to indicate the core. And inductors overall exhibit the property of induction. Inductance is the opposition to a change in current flow. So this is inherently an electromagnetic type of device. What we're going to be looking at requires a background understanding of how electromagnetic flux moves and what its properties are when we have interaction with electrical circuits. Inductance is measured in henries. That's what would be on the nameplate of a coil or inductive coil. And when we have inductance within an electrical equation, or any equation for that matter, it's represented with the letter L. So let's see what properties affect inductance in an inductor. So here's our equation. L is equal to N squared mu A over L length. First thing is inductance, measured in henries, is equal to the number of turns of wire in the coil squared, multiplied by the permeability of the core. That's not something we're typically going to measure or do calculations with, but permeability is the ability of a device to concentrate magnetic lines of flux when compared to air. How about the area of the core? How large is it? And finally, the length of the magnetic field. Now remember, with any type of equation, variables on the bottom are inversely proportional to the variable being calculated, which means as the length increases in value, L, inductance, will get smaller. Whereas any of these properties up here, if they are increased in value, the inductance will go up or increase. This is a great diagram simply to show the 1, 2, 3, 4 different factors that will affect inductance. More turns of wire, higher permeability to magnetic lines of flux, a larger core area, and finally a shorter path. All of these would lead to higher inductance. So how does an inductor react when it's connected to a DC circuit? Well, there's some interesting things that take place, and we need to have a good understanding of how electromagnetic flux functions. And because of that, we're going to start with Faraday's law of induction. Voltage, or an EMF, is induced on a conductor if there is relative motion between it and a magnetic field. Remember, relative motion means we could have a conductor moving through a magnetic field, or we could have the magnetic field moving across the conductor. It doesn't really matter which one. Either way, relative motion exists and the voltage is induced onto the conductor. Now remember, when we have current flowing through a conductor, there will be concentric lines of flux that will surround that conductor in either an AC or a DC circuit. Those lines of flux travel in either a clockwise or counterclockwise direction. So when we take a conductor and we put it into a DC circuit and we energize it, what we would expect to see is an increase or an expansion of the magnetic lines of flux. The magnetic field will expand. Once it's reached its full value of current, we would say the DC circuit was fully energized, and the magnetic field would remain static. And the reason it would stay static is because the current value within the circuit has not changed. It's going to remain at that steady value because it is direct current. When the DC circuit de-energizes, we would expect to see the magnetic field collapsing. And so it would shrink down until eventually there was no current within the circuit. So these concepts are important because what we're going to be talking about is a concept of self-induction. And self-induction happens within inductors, and it helps to prove why they react in certain ways within a DC or an AC circuit. So self-induction is the interaction of flux between multiple turns of one coil. Lenz's law is going to be used to help describe what's happening in this situation. And Lenz's law stated that an induced voltage would cause a current to flow in such a direction that its magnetic effect would oppose the change that produced it. Oh man, that's a mouthful. And what that simply means is that when we generate a voltage, that voltage will want to oppose the initial source that created it. Kind of a mouthful when it comes to a definition. Let's see how it's actually applied. Remember, relative motion will be important throughout this discussion. Relative motion is what's going to prove why the inductor reacts the way it does. So let's take a look at two conductors that are side by side. This conductor here will be in a DC circuit, and this one over here is going to be sitting right beside it, and we can think of this as multiple turns to a coil, or simply just a second conductor sitting beside an energized one. So first, expansion of magnetic lines of flux as the circuit energizes. Is there relative motion between this conductor and the magnetic lines of flux? Of course there is, right? We could prove it with Fleming's left-hand rule. And Fleming's left-hand rule would have us pointing our index finger down, have us moving or pointing the thumb towards the center or energized conductor, and then current flow would be the middle finger pointing into your computer screen, which would mean current flowing away. In a coil or an inductor, the same thing will take place. So as we have magnetic lines of flux increasing or expanding because of current flow, we will see the expansion of it at each turn of the coil. Now, an interesting thing takes place, and we're talking about nanoseconds here. As the magnetic flux expands here, it will start to break across the next turn of the coil. And what will that do? Well, we just looked at an animation. It will cause a current to flow in the opposite direction, but it's on the same conductor, which is kind of weird. So let's see how this takes place. We're energizing the circuit. Magnetic flux is expanding. It cuts across the second turn of my coil. We said there's relative motion, and what happens with relative motion is a voltage is induced. And we said from the previous animation that magnetic flux will cause a current to flow in the opposite direction. So look what happens. It's actually producing electromagnetic flux around this little turn of the conductor because we have induced a voltage into it and caused current to flow. Well, what's going to happen? Well, you really have two values of current now. You have the main current, which is from the source, and you have this really small current here, which we could say is the counter current, or the current that's produced by the counter EMF. Now, which one is larger? Of course, the main source current is larger, but what it's going to do is it's going to take longer for the current, the main source current, to reach its peak value. Once this current reaches the second turn of my coil, well, obviously it overcomes and that counter EMF disappears. So counter EMF opposes the main circuit current from reaching its max value immediately. So when the circuit is energizing, counter EMF, because of breaking of lines of flux, is going to oppose circuit current from reaching its maximum value immediately. But it's only going to be present, counter EMF, when there is relative motion. Remember, relative motion has to do with the increasing value of current. So once the inductor in a DC circuit has reached its peak value of current, or its steady state value is what we refer to it as, there would be no counter EMF. And the reason there's no counter EMF is because there is no relative motion of magnetic flux on each of the turns of conductor in the coil. Remember, counter EMF is only produced when there's relative motion between magnetic lines of flux and a conductor. So what happens when I de-energize the circuit? An odd thing takes place. When I de-energize the circuit, remember this conductor here is connected to my source. What that will have an effect on is collapsing magnetic lines of flux. Those will cut across this conductor. And what that will cause is an increase in the value of voltage induced into this conductor. Isn't that nuts? It will actually cause an increase. Let's look at that again. You can actually use Fleming's left-hand rule to prove this. So counter EMF doesn't mean that the current will flow in the opposite direction. Counter EMF simply means it opposes the initial source circuit. So what is it going to oppose? It's going to oppose the current from dropping to zero very quickly. It's going to make it slower. So again, watch. As this current gets smaller because I've turned off the circuit, this one gets larger. And so what ends up happening is we generate a little bit of residual current, but a larger voltage. A great explanation of this is found on the YouTube channel, The Engineering Mindset, and it shows an inductor illustrated as a water wheel with a large flywheel connected to it on the back side. It acts almost the same, and I like this analogy because when I push water through it, it would take time for this to reach full speed, and in effect, it would be limiting the speed of the current through the water wheel until the water wheel reached that steady state value. And when we wanted to turn off the current flow, what would happen? The paddle wheel would keep turning for a little bit, trying to push current through the system. I encourage you to take a look at that video if you have not done so already. That brings us to the end of part 1 of inductors and inductance.